Okay, welcome to Chapter 18, Section 2. We're going to look at convex and concave lenses, and we're going to look at how lenses can be used to enlarge or reduce images. So we're going to look at this idea of real and virtual images again, and we want to see where the images are located. We're going to use ray diagrams to locate the image again. Transparent just simply means that the light goes through it. Might be affected because of the index of refraction, but all the light goes through it. We're going to look at lenses. We're going to look at the idea of a convex lens, a concave lens, and a thin lens, the thin lens equation. We're going to get into it in a minute, but basically between convex and concave lens, the way I remember it is concave are the ones that are caved in, and convex has to be the other one. So let's take a look at a lens. A lens then is simply a piece of transparent material, could be glass or plastic, and it's used to focus light to form an image, and either one or both surfaces can be curved. So let's take a look at a convex lens that's thicker in the middle. See the rays come in, if the rays come in parallel, then they're going to be focused to a spot out here. This is going to be the focal point of this particular lens. Since it basically this type of lens takes parallel lines and focuses it on a point, we call this converging, coming together. Because when surrounded by material with a lower index of refraction, like air, it refracts parallel rays of light so that the rays meet at a point. And then we get the caved-in lens that is thinner in the middle. When the rays come in parallel to that, they always get spread out. Since they spread out, we call this a diverging lens because, again, when surrounded by material with a lower index of refraction like air, the rays passing through it will tend to spread out. Light passes through a lens, refraction occurs because when it meets the two surfaces, we can use Snell's law and geometry and all that kind of stuff to predict the path. But we're actually going to simplify it and assume that the refraction occurs on a plane that we're going to call the principal plane. So when we draw our diagrams, we're going to look at a principal plane and a principal axis. This approximation is called the thin lens model. It makes life a little bit easier, so we're not doing Snell's law all the time. As we've talked about before, if you have a lens, you can focus the rays from the sun on a piece of paper, and you can get it to ignite. All the rays are coming in at this point pretty much parallel from the sun. Technically that they are still diverging slightly, but we're so far away from the sun that by and large all the rays that we're seeing can be thought of as parallel. If you flip the lens around, it would work basically the same way. So let's take a look at what happens when you're trying to form an image. Now we're not talking about the rays coming in parallel. We're talking about, once again, we're going to focus on two rays. But let's take a quick look at the video. Quick look at the video. And here it goes.
In this animation, rays are traced from an object being viewed from a convex lens. For the purpose of locating the image, you only need to use two rays. Ray 1 is parallel to the principal axis. It refracts and passes through F on the other side of the lens. Ray 2 passes through F on its way to the lens. After refraction, its path is parallel to the principal axis. The two rays intersect at a point beyond F and locate the image. Rays selected from other points on the object converge at corresponding points to form the complete image. Note that this is a real image that is inverted and smaller compared to the object. If a refracted ray is reversed in direction, it will follow its original path in the reverse direction. This means that the image and object may be interchanged by changing the direction of the rays. Let us consider that the object is at a distance of 15 centimeters from the right side of the lens. If the path of light through the lens is reversed, the new image, located 30 centimeters from the left side of the lens, is a real image that is inverted and larger compared to the object. If the object is placed at twice the focal length from the lens at the point 2f, the image also is found at 2f. Because of symmetry, the image and object have the same size. Thus, you can conclude that if an object is more than twice the focal length from the lens, the image is smaller than the object. If the object is between f and 2f, then the image is larger than the object.
Okay, and we're going to talk about what happens when the image is either at f or between f and the lens in a minute. So let's continue on. Get rid of this. Again, when the object is placed at the focal point of the convex lens, then basically all of the rays end up being parallel, so there's no image. No image gets formed. When you put the image in closer to the lens, then the rays will start to diverge coming out the other side, and what you get is an image is formed, but it's a virtual image and it's on the same side as the object, and it's larger. So kind of like with the mirror, again, depending on where you put the mirror as to whether it makes it right side up or upside down, and so on and so forth. So here we have, again, if we put it in closer to the focal point, we look at our two rays. The one ray that's parallel to the principal axis will go through this principal plane and and be directed down towards the focal point. If you have one that's coming in at an angle that would have passed through the focal point on the same side as the object and hits the ray, basically that one is the one that gets parallel. So here we can see that these are spreading out. No image forms on this side, but if you backtrack them, you'll see that a virtual image is formed over on the other side. Virtual image, again, is larger than the object. That's how a microscope works. And so here again, we have ray 1, ray 2. This just kind of talks you through what I just talked about. So if you want to take a look at those, you could look at those, but I've already explained them. And so again, no real image is possible, but if you draw the lines back, you get the virtual image. And it's on the same side as the object, and it's larger, and it's the same orientation, it's right side up. Okay, so that's the convex lens. Again, you can determine the location by drawing the rays. Okay, so now let's look at a concave lens. What happens with a concave lens? Well, again, the ray that goes in that would have passed through the focal point on the far side gets angled so that it comes out of the ray, out of the lens parallel to the principal axis. The ray that is coming in parallel appears to have been originated at the focal point and coming off at an angle like that. So you can see that these rays then are spreading out, and they don't form an image over on this side, but if you backtrack them, they do find a point of intersection back here, essentially a virtual image. It makes the image smaller. So you get a virtual image, same size, the same side as the object, and smaller, same orientation. Again, this is just going to walk you through the rays. If you want to read through this, you can see what it's talking about with the rays. Ray 2, again, is the one that would have passed through the focal point on the far side, comes out parallel. And if you sight those back, you could see where the image would have formed, and it produces a virtual image. Image is located at a point from where the two rays apparently diverge, apparently start at. The image is upright, smaller, and compared to the object. This is true no matter how far the lens is from the object. So with concave lenses, it makes a big difference where the image is in relationship to the focal point and twice the focal point and so on. Concave lenses, it doesn't really make any difference where the object is. It's always going to be smaller, and it's going to be a virtual image. So when you're solving problems with a concave lens, using the thin lens equation, you should remember that the sign convention for the focal length is different from a convex lens. The focal point of a concave lens is 24 centimeters from the lens. The F value is a negative, indicating that it is a concave, not a convex lens. All the images for the concave lens are virtual, thus the image distance is given at 20 centimeters. Should be the distance of the image is a negative 20. The object position is always positive. Okay. So problems involving spherical lenses. The lenses have a face that have the same curvature as a sphere, and so we could think of this as other simplifications. Anyways, we're just going to use the thin lens equation. Hopefully this looks familiar to you, because this is exactly the same formula as we use for the mirror. It doesn't matter, concave or convex, works the same. The inverse of the focal length of the spherical lens is equal to the sum of the inverses of the images and the object. Magnification can also be calculated, and again, hopefully this is still familiar to you, because this essentially is the same magnification we use as for convex and concave mirrors. So the magnification, defined as the image height divided by the object height, is equal to the negative of the image position and the object position. And again, the big thing here is to remember the sign convention. You may want to take a closer look at this at some point. This chart is in your book, but again, instead of trying to remember all this stuff, I think you're better off just drawing the images and drawing the ray diagrams and figuring out what you got, and then work from there. Okay, so distance from the principal plane of the image has a focal point of F. The focal length depends on the shape of the lens and the index of refraction of the material. The focal length and the image positions can be negative. And for lenses, virtual images are always on the same side as the object. Real images are on the other side as the object. In virtual images, again, the convention is that we're going to say that the distance is a negative. Okay, so the absolute value of magnification between 1 and 0. Magnification is with absolute values greater than 1 represent an object is larger. And negative magnification simply means that the image is inverted compared to the object. And so the concave lens produces only virtual images, whereas convex lenses, again, it could either be virtual or real, inverted or right side up, and so on. So let's focus on a convex lens. Here we have an object is placed 32 centimeters from a convex lens that has a focal length of 8 centimeters. So if F is equal to 8, 2F would be 16. So we know that this is way beyond 2F. So we're going to ask a question about where does the image form. If the object is 3 centimeters high, how tall is the image? And what is the orientation of the image? In other words, is it point in the same direction as the original image, or is it upside down? So we're going to sketch our diagram. So we start with our principal axis and our principal plane. We put our object out beyond 2F, and we draw our object. Remember, this is going to be 3 centimeters tall. This XO is 30 centimeters. We have a ray that comes in parallel to the principal axis, and it would be diverted as if it was going to go through the focal point on the far side. This one actually goes through the near focal point. When it goes through the near focal point, here it's the mirror, it gets diverted out, so it's coming out parallel. So that's basically the image that we need to keep in our mind, and we can see where those 2 points converge. That's essentially where we're going to have our image being formed. So here's all our numbers, and here's what we're going to try to figure out. where's the image and how high the image is. We're going to use our thin lens equation. They're going to manipulate it again. So they've already manipulated it, and then they plugged in the numbers. I would suggest that you just use the numbers, plug in the numbers first, and then solve for xi. Either way, you're going to come out with 11 centimeters. So 11 centimeters from the object, it's a positive number, so it's on the opposite side of the lens. We're going to use our magnification. We're going to substitute in our 11 over here. Over 30, it's going to tell us what the magnification is. This again is a ratio. We know that this number down here is going to be a 3, and we're solving for this number up here. Again, you could plug these numbers in and then solve for x, or you can manipulate the equation and then plug in the numbers. Either way, remember that you're using a negative xi, which essentially means that we're probably going to end up with an inverted image. We end up with a -1, so it makes it smaller. We expect it to be smaller. We expect it to be inverted. We expect it to be negative. And that's it. Thank you very much.